Welcome back to this module on pipelining. In this final lesson in this module, I will present an exercise that shows how code will be executed on the canonical 5-stage pipeline. Finally, an exercise. I want to know how the code shown here on the right will be executed on the canonical 5-stage pipeline with full forwarding hardware. With full forwarding hardware, I mean that anything that can be forwarded will be forwarded. You should show how the code will be executed by filling out the table at the bottom of this slide. The first column shows the instruction. The second to 12th column depict clock cycles. In particular, you have to place the shortcuts IF, ID, X, MEM or WB in a box if the instruction in the first column is in that stage during that particular cycle. Furthermore, if a stall happens, for whatever reasons, during a cycle, place a cross in the box or in the boxes. Finally, if forwarding happens, draw an arrow from the pipeline stage that currently contains the result to the pipeline stage consuming the result. I recommend you to do this exercise yourself before watching the solution. If you want to do so, please pause the video now. Please press the pause button. Welcome back. Let's see if your solution matches mine. There is no guarantee, however, that my solution is correct. The first instruction, the shift left logical, is not dependent on anything, so it will flow through its pipeline stages without any delay. The second instruction, the add R3, R2, R3, is dependent on the preceding shift left logical through the R3 register. This dependency is resolved by forwarding the result from the execute stage of the shift left logical to the execute stage of the add instruction as indicated by the arrow. The third instruction, the load word R40R3, is dependent on the second instruction. The result produced by the second instruction in R3 is needed in the execute stage of the load word, since the effective memory address is calculated in that state. Therefore, again, forwarding happens from the execute stage of the second instruction to the execute stage of the third instruction. The fourth instruction, the load word R5 for R3, also needs R3 to calculate the address, so it is also dependent on the second instruction. But in this case, the result is not forwarded from the X stage of the second instruction, but from its MEM stage, as indicated by the arrow. Next is the instruction stall word R50R3. This case is particularly interesting because it is dependent both on the load that immediately precedes it to register R5, as well as on the second instruction, the add through the R3 register. The first two stages, IF and ID, execute in their designated execution cycles. Then comes the X stage. Do we need forwarding here? The answer is no. In the execute stage of the stall word, the effective address is calculated. For this, register R3 is needed, and this register has already been written back in clock cycle 6 during the write back stage of the add instruction. So no forwarding to this stage is needed. Then comes the MEM stage. In this stage, R5 is written to memory. Since R5 is loaded by the preceding load word instruction, do we need a stall cycle there? Does this situation correspond to a load use data hazard? The answer is again no. We can forward from the MEM stage of the load in which R5 is loaded from memory to the MEM stage of the store. Remember that I assume full forwarding hardware, meaning that anything that can be forwarded will be forwarded, and this is such a case. Finally, the write back of the store, even though nothing happens in that stage, occurs in the next designated clock cycle. And finally, the pipeline stages of the sixth and final instruction, stall word or for R3, occur in their designated cycles without stalls and without forwarding. So we see that all stall cycles can be avoided in this example by forwarding. One additional exercise. We have the following code: add R1, R2, R3, then branch if equals 0, R1 to label 1. Then a knob in the stall cycle. Then an OR, and then some other code. The question now is, can the OR instruction be moved into the branch delay slot? If it cannot, how can we modify the code so that the OR can be scheduled in the branch delay slot? In either case, yes or no, you should be able to explain your answer. This time, I will not provide the answer to this question. By doing so, I hope to motivate you to find an answer for yourself, perhaps together with other people you may find online. Have fun. This completes this lesson. Thanks for watching. In the next lesson, I will start a new module in which we will extend the canonical pipeline with multi-cycle operations. Hope to see you back.